Welcome to this video on computer organization and architecture. We'll be exploring the fundamentals of computer design, covering topics from abstract architecture to hardware organization. This video, titled The Silicon Symphony, will deconstruct the machine. We'll examine how logical definitions, physical wiring, and memory hierarchies converge to create computation. Computer architecture and computer organization are two sides of the same coin. Computer architecture represents the promise made to the programmer. It defines what is visible at the programming level, such as the instruction set, input-output mechanisms, and addressing modes. In simple terms, architecture is the interface the programmer interacts with. Computer organization, on the other hand, is the hardware engine. It describes how the architecture is actually implemented, using operational units, control signals, memory interfaces, and circuitry. Organization explains how the machine works under the hood. The key insight here is this: the same computer architecture can be implemented using totally different organizations. For example, processors may share the same architecture, yet differ significantly in performance and internal design due to different organizational choices. The core system components include the central processing unit, main memory, and input/output. These are all interconnected by the system bus, which includes the data, address, and control buses. The stored program concept means instructions and data reside in the same memory. Data representation distinguishes bits based on context. Opcodes are the command, and operands are the target. The control unit of a processor can be implemented using two main approaches. The first is hardwired control. In this approach, control signals are generated using fixed logic circuits. Because there is no intermediate software layer, execution is extremely fast. This method is therefore commonly associated with RISC architectures. However, the limitation is inflexibility. Any modification requires hardware redesign. The second approach is microprogram control. Here, control signals are generated using micro-instructions stored in control memory. This makes the design more flexible and easier to modify or debug. For this reason, microprogrammed control is typically associated with CISC architectures. The trade-off is slightly slower execution compared to hardwired control. In summary, hardwired control prioritizes speed, while microprogrammed control prioritizes flexibility. The boot process begins when the system is powered on. Power on initiates the startup sequence and activates the ROM. From ROM, the BIOS is executed, which performs basic hardware initialization and configuration. Next, the system runs the power on self-test, or POST. POST checks critical components such as RAM, storage devices, keyboard, and display for errors. Once the system passes POST successfully, the bootstrap loader takes control. The bootstrap locates the operating system, loads it into main memory, and finally transfers control to the OS. At this point, the system is ready for normal operation. To understand modern computer systems, we must first understand the vocabulary of data scale. In computing, data units grow exponentially. 1 kilobyte is equal to 2 to the power of 10. 1 megabyte is 2 to the power of 20. 1 gigabyte is 2 to the power of 30. And this scaling continues up to terabytes and petabytes. As data size increases, a major challenge appears: the speed gap. The CPU operates at extremely high speed, while main memory is comparatively slower. This difference creates a performance bottleneck. To solve this problem, cache memory is introduced. Cache memory acts as a high-speed bridge between the CPU and main memory, reducing access latency and ensuring faster data availability for the processor. Cache mapping determines how data blocks are placed. Options range from simple direct mapping to flexible associative mapping, with set associative mapping providing a balance between the two. A case study compares row major versus column major access. Row major access provides high spatial locality, while column major, or strided access, results in low spatial locality. Analyzing the impact mathematically, the strided access pattern, P2, generates 16 times more cache misses than the sequential access pattern, P1. This highlights the importance of spatial locality. In summary, computer design involves structure, control, and optimization. Good optimization requires understanding the memory hierarchy, particularly spatial locality, to minimize cache misses. The final thought is that great software design relies on understanding the hardware reality beneath it. Thank you for watching this video.